Yes, for the entire session, I will ask you to turn on the camera and turn off the microphone to avoid any disturbances. Yeah. All right, the time is shown 2 p.m. sharp, so I will open this plenary session. First of all, I would like to express my gratitude to all the ladies and gentlemen, Madam Speaker, distinguished guests, students, and ladies and gentlemen for attending this ICIMECE 2021. And this session will be delivered by two keynote speakers. The first speaker will be delivered by Dr. Noni Soraya Sambudi and will be continued by Associate Professor Abdul Hakim Al-Majid. We are pleased to have you here, Dr. Noni and Associate Professor Abdul Hakim Al-Majid at ICIMECE 2021. I hope you have a pleasant day so far. And first, I would like to greet Dr. Noni Soraya. Thank you for attending the ICIMECE today. So how are you?
Thank you. I'm doing well.
Okay, that's glad to hear. And before we start, I'm sorry, I forgot to introduce myself. I will be the moderator for this plenary too. My name is Aditya Muhammad Nur. You can call me shortly as Aditya. Before we enter the first presentation by Dr. Noni Soraya, let me walk you through the short portfolio of Dr. Noni Soraya. Dr. Noni Soraya Sambudi obtained a PhD from Korea Advanced Institute of Science and Technology, and she currently works at the Department of Chemical Engineering, University Technology Petronas. Dr. Noni does research in composite fibers, photocatalysis, carbon dots, degradation of organic pollutant, and also biomaterials. And today, Dr. Noni Soraya will present her work with the title of The Utilization of Carbon Quantum Dots for Photocatalytic Degradation. So, Dr. Noni Soraya, if you are ready with your presentation, the screen is all yours. Thank you.
Thank you very much, Mr. Aditya, for a very nice introduction. Okay, so I will just share my presentation file that I have prepared. Okay. Okay, so I hope you can see the slide that I share. Okay.
Yes, I can see it clearly.
Okay, very nice. So first of all, I would like to thank Universitas 11 Maret for actually arranging this very nice conference and to invite me to share my research results with all of the audience over here. So as mentioned by Mr. Aditya, I work in photocatalytic degradation and also for the synthesis material that is actually meant for this purpose. Okay, so the title of the presentation that I will bring today is about the utilization of the carbon quantum dots for the photocatalytic degradation. So in order to properly start the presentation, I would like to introduce you with the quantum dots. Many of you, I think, have already heard about the quantum dots, right? The main usually utilization of the quantum dots is usually for the display, yeah, especially for the LED display. Okay, but quantum dots actually has an organic form, which we call it as the carbon quantum dots, or abbreviated also as QD. What is actually quantum dots? Quantum dots is very small materials with size usually less than 10 nanometer. And these quantum dots actually can emit certain type of colors under irradiation of light. In the case of the carbon quantum dot, as I mentioned, it is the organic type of the quantum dots, right? And the carbon quantum dots especially is very unique because we can actually modify the surface of the carbon quantum dots with various functional groups, such as hydroxyl, carboxyl, and also amine. So in the practical application, carbon quantum dot has been applied so far, especially for bioimaging and biosensing usually. The introduction of the carbon quantum dots into the photocatalytic world is actually still quite new. We still have quite limited research that actually involve the carbon quantum dots into the photocatalytic degradation application. Not only photocatalytic degradation, it can also be used for photocatalytic hydrogen generation or even CO2 photoconversion. So as I mentioned, the size of the quantum dot itself is very small, less than 10 nanometers. Actually, that makes the name appear as quantum dots in the origin. Okay, because of the size, yeah, less than 10 nanometer, the size of the quantum dots is actually quite similar with the Bohr radius. Okay. So the Bohr radius actually has the size from 2 to 10 nanometer. Right? Due to this size, the quantum dot actually has very specific or unique characteristic. Okay. Due to the size, right, which is less than 10 nanometer, there is quantum confinement effect that is possessed by the quantum dots. Okay. First of all, with the size, the lesser the size of the quantum dots, right, it will gives us the higher energy band gap between the valence band and the conduction band. Okay. So, and also, the lesser the size of the carbon of the quantum dots, it will gives us the blue shift. The blue shift, which means that the quantum dot itself is sensitive. It's more sensitive in the UV region. Okay, yeah? So by actually modifying the size of the quantum dot itself, we can actually tune the energy gap of the quantum dots and also the shift in the wavelength of the quantum dots. We can actually engineer or modify the size of the quantum dots for it to be sensitive, either with the visible light irradiation or with the UV light irradiation. Okay. So the size of this quantum dot actually gives this kind of unique properties. The carbon quantum dot itself, speaking about the carbon quantum dots, we can actually synthesize these carbon quantum dots from any kind of material that contains carbon. The most common materials that we use to convert to carbon quantum dots is actually biomass, due to the abundance of the biomass. So we can actually apply several techniques in order to convert this biomass into carbon quantum dot. So what kind of synthesis method that we can use? First of all, we can use the hydrothermal method, right? We can apply certain temperature, certain high temperature into this solution containing carbon precursor. At the end of the reaction, we will get the carbon quantum dots. The other technology that we can apply, or the other process, is by using the microwave assisted synthesis. Pyrolysis synthesis can also be used to synthesize the carbon quantum dots. Not only the one that I show in this slide, actually there are many other synthesis approaches that we can use to convert biomass into carbon quantum dots, even by using laser. So the application of the carbon quantum dot so far has touched so many aspects. Not only the bioimaging and also biosensing, it also has been used for the battery, supercapacitor, as well as the photovoltaics. Okay. So the application that I am very interested regarding the carbon quantum dots is actually in the photocatalytic degradation area. The photocatalytic degradation itself, right, in the current trend, we are still dealing with how we can modify the photocatalyst to be sensitive under the irradiation of visible light. Okay, why visible light? As you can see in the solar spectrum that is received on the surface of the Earth, actually when the sun irradiates the Earth, we receive most highly percentage of the sun are in the visible light area. The UV light area actually only consists, only comprised to 2 to 5% of the overall sun spectrum. Okay. So the research now is still dealing with how we can actually modify the photocatalyst for it to be able to harvest the light that comes from the visible light area. Okay. And if you work in the photocatalytic degradation area, then you recognize this kind of diagram. So we show this kind of diagram actually to show what happened during the photocatalytic process. So when the photocatalyst actually receive light from the sun or from other light source, the electron from the valence bands will jump into the conduction band, or we can say that it is in the excited state. And what is expected for these electrons is for them to actually undergo the reduction process. So from the reduction process, we can form the superoxide, right? While the hole that remains in the valence band actually can form the hydroxyl radical. These radicals actually are important if we want to reduce, if you want to degrade certain organic pollutant, right? Because these pollutants are our weapon in order to attack the organic pollutant, which then degrade them. The full degradation, we expect it to consist of only CO2 and also water, right? But actually the reduction and also the oxidation process experience challenge, which is the competing reaction, which is the recombination of electron and hole, right? So the electron actually tends to be stable, right? So they actually like to recombine like to recombine with the hole in the valence bands. So in order for us to actually tackle this problem, we try to modify the photocatalyst agent itself, right? So in this research, what we did actually was we tried to incorporate the carbon quantum dots into the system of the photocatalyst. So we can use any type of photocatalyst such as titanium, tungsten oxide, or other photocatalysts, and we can use these carbon quantum dots as the sensitizer, as a sensitizer that can absorb the visible light from the solar spectrum. Right? Because many type of the photocatalyst actually has quite low performance under visible light, because due to the band gap that they have, they can only receive UV light. Okay, so we can modify this type of photocatalyst by incorporating the carbon quantum dots. But before we are going to that direction, we wanted to actually test the performance of the carbon quantum dot itself in sole use, only carbon quantum dots, whether the sole use of carbon quantum dots actually can perform photodegradation. Okay, so firstly, we did experiment actually by synthesizing these carbon quantum dots by using rice husk. So we used the hydrothermal method at this range of temperature and also pH. And from the experiment, we got our carbon quantum dots with size less than 5 nanometer. Okay, right. Then we actually tried to degrade the methylene blue. We tried the colorization of the methylene blue around 10 ppm under visible light radiation by using this quantum dots synthesis from the rice husk. Okay, so the best performance that we can get is actually after more than 4.5 hours, we can degrade almost fully degrade around 10 ppm of the methylene blue. Yeah. So from this result, we see, okay, actually this carbon quantum dots has the ability to do the photodegradation in sole use. So what can we move from here? Okay, so we want to try, what if we try to modify this carbon quantum dots, right? What if we do the doping? Will the performance of the carbon quantum dot actually increase in the sole use? Okay, so we try to dope the carbon quantum dots. So we try to dope it with the non-metal and also metal, right? And why the doping method is actually beneficial? Actually, it has been widely researched that the doping of the material can actually enhance the quantum yield of the material, right? It can also narrow the band gap, right? That will induce the excitation of electron faster into the conduction band. So we hope that it can improve the performance of the material for the photocatalytic process. Okay. So we try to dope the carbon quantum dots by using nitrogen as the non-metal source and also bismuth as the metal source. So what we actually observe after the doping is the one that we dope with the bismuth actually has a blue shift. It goes to the UV light area, while the one that we dope with the nitrogen actually is going red shift. So it goes to the visible light area. So after we actually test for the photodegradation test, again by using the same 10 ppm methylene blue, right? It shows that the nitrogen that is doped with the carbon quantum dots has the the best performance. It can reduce around 70% of the methylene blue after 4.5 hours. Okay, right? So if we see, actually when we dope, the performance is not better than the undoped particle of the carbon quantum dots. So from here, we can see that the sole use of the CQDs is actually very limited, very limited in doing its task. Okay, so we agree with the strategy that is done by the other scientists. It is better for us to actually use the carbon quantum dots in combination with other photocatalysts. So the CQD can do its job as sensitizer. Okay, so what we do next, we combine these carbon quantum dots with the titania, right? So we hope that, that the titania that has already been decorated on its surface with the carbon quantum dots, right? The carbon quantum dots can actually act as a bed for the electron that's already excited to reside in the carbon quantum dot, and then to later produce the radicals through the reduction process. Okay. And in the combination of the carbon quantum dots that we have already synthesized from the rice husk, we combine it with titania, and then we try to actually this time to degrade the acetaminophen. Right? And this time we try to be more ambitious. So we actually did the experiment under the sunlight irradiation. Okay, so before we go to the performance, right? So what are the analysis? What are the characteristics of the combination of these carbon quantum dots and titania that we found? Based on the surface area, actually, we found that the surface area of the titania can be improved when we incorporate the carbon quantum dots into the matrix of the titania. Okay. So we see that the surface area is optimum when we incorporate 1% of the carbon quantum dots. Right? But by the increasing of the carbon quantum dots, the further increasing, what we found is the surface area actually decreasing. So what we see from here, maybe there are agglomeration during the mixing process in the precursor step. So the mixing process might not be well distributed because the carbon quantum themselves, they tend to aggregate to each other, right? So if we increase the amount of carbon quantum dots, we think that we might get high agglomeration that actually decrease the surface area of the composite itself. Okay. So the incorporation of the carbon quantum dot also in the titania can actually reduce the band gap further. So this actually indicates a good property, the decreasing of the band gap, meaning that we can go to the visible light area sensitivity, which means that the composite material actually is now more able to harvest the visible light from the sun. So based on the performance, to remove the acetaminophen, actually we found that the 1% addition of the carbon quantum dots into the titania gives us the most optimum results. So after 4 hours under the sun irradiation, we actually can have a full degradation of the 5 ppm acetaminophen. So the material is still effective if we use it for higher concentration of the acetaminophen. For the 10 ppm of the acetaminophen, it can be fully degraded after 6 hours. If it reached 20 ppm, then we actually need longer time for the material to actually perform the degradation process. Okay. From here, we are quite excited to see the results that our material actually is quite active under sunlight irradiation. So what we do next is we are interested if we actually can find or can observe the same phenomena if we use another photocatalytic agent other than titania. Okay. So what we try next, we use tungsten oxide. So we try to combine these carbon quantum dots with the tungsten oxide. Okay, so this time we want to do a dop carbon quantum dots. So previously we doped with the nitrogen. From that doping result, we want to combine it with the tungsten oxide. This time we have different source that we use to synthesize the carbon quantum dots. So we use the sugarcane bagasse. So previously we used the rice husk, now we use the sugarcane bagasse. And this image over here, the one that shows layer structure is the tungsten oxide. So the nitrogen dot carbon quantum dot is expected to be available on the surface of the tungsten oxide, so it decorates the tungsten oxide, which is the same actually, which is the same modification or the same structure as what we have with the titania, yeah, the combination of carbon quantum dots with titania. Okay. In case of photoluminescence, right, what we have is the decreasing photoluminescence spectra when we incorporate the carbon quantum dots into the matrix of the tungsten oxide. Okay, so based on the reading that we did, actually when we have a lower photoluminescence intensity, it can indicate that the recombination of the charge can be reduced, right? Since the recombination of charge can be reduced, it's a good news, meaning that if the recombination is reduced, then we will have more reaction of reduction and oxidation can happen to the photocatalytic material. Okay, but we have to prove it with the experimental result. Okay, so this is the experimental result that, that we did. Actually, there is preliminary results that I didn't show, but based on our previous experiment, we found that the photocatalytic performance of the tungsten oxide is the most optimum when we incorporate around 2.5% of the nitrogen dot carbon quantum dots. Okay, so the performance of the methylene blue degradation, right, and when we use this material, the nitrogen dot carbon quantum dots with tungsten oxide, actually we can expect a very sharp degradation after 30 minutes. So after 30 minutes, we found that the methylene blue has already been degraded to more than 90%. Okay. So roughly from here, we can say that the performance of the carbon quantum dots when it is combined with the tungsten oxide is much better, yeah, with the solely use of the carbon quantum dots itself. So we also tested the material to degrade the same methylene blue, but we increased the concentration up to 50 ppm. Yeah. Even until 50 ppm, we still can get around 70% degradation. Yeah. Okay, and then after that, we try to recycle the material. Right? But we only did until 3 recycle tests. Right? So until 3 recycle tests, we actually can keep the performance of the material to be more than 80%. Yeah? So we still can remove 80% of the methylene blue from the solution. Yeah? Even if we reuse the material until 3 times. Okay, so by seeing this actually excellent performance from the combination of nitrogen dot carbon quantum dots and also tungsten oxide, we think of doing another application upon this material. So we decide to actually immobilize this material into polymer fiber. We decided to actually immobilize it into polymer fiber, and we want to make an oleophilic fibers mat. These oleophilic fiber mats can be used actually to separate oil from water, right? So this can be our preliminary study in order for us to venture maybe in the new direction or in the new application of treating the oil spill in the future. Okay, so what we found when we actually incorporate these carbon quantum dots that we combine with tungsten oxide into the PLA fibers. So we use polylactic acid as the polymer source, right? So when we incorporate these carbon quantum dots and tungsten oxide into the fibers, we actually can absorb the oil. We can absorb the hydrocarbon into the fiber mats, right? Okay, so how actually we form the fiber? So we use electrospinning. We just actually mix this material in the solid form, the combination of the carbon quantum dots and also tungsten oxide. We mix with the polymer solution, and then we spin it into fiber by using the electrospinning. Okay. So based on the spinning results, right, the contact angle of the polymer itself is increasing, right? So it can reach around 130 degrees when we incorporate this material into the polymer fiber. So the increasing of the contact angle makes the fiber mats to become hydrophobic and oleophilic. So it absorbs the oil, but it rejects the water. Okay, so we try to separate the heptane, hexane, and hexadecane from the water mixture. And from the test that we did related with the oil absorption capacity of the fibers, the one that we incorporate with the tungsten oxide and also carbon quantum dot shows higher oil absorption capacity compared to the just pristine polylactic acid. Okay, and also actually the hydrophobicity and also the oleophilicity of the fiber mats actually can increase the flux, which is they increase the flux of the heptane, hexane, and hexadecane that goes through the fiber mats. Right? So overall, we can actually separate the hydrocarbon, right, from the water fully, almost 100%, and we actually get a good flux from the separation performance. Okay. Then we want to see whether the fiber mat is actually stable enough to do its job if we actually reuse it several times. Okay. And then we try to actually recycle the fiber around 10 times and we still get a consistent flux, around more than 8,000 liters per meter square hour. Okay, so we use this recycle performance for the mixture of the hexane and also water. So from here, we can see that the fiber that we made actually is quite stable to be used around 10 times to separate the hydrocarbon from water. Okay, right. So at the same time, we want to see on whether if we incorporate this material into the polymer fiber, whether the photocatalytic ability of this material is actually still intake or decrease. Okay. So again, we did the decolorization performance, decolorization test. We use the same methylene blue solution. Okay. So this is for the 5 ppm performance. We can reach around 90%, 90% of the decolorization in less than 30 minutes. So meaning that actually the photocatalytic performance of the materials in the fiber actually still intact. Okay, So we also test the same performance by using other concentration of the methylene blue. So we increase until 50 ppm. So for the 50 ppm, we can reach around less than 40%, less than 40% of the decolorization, right, after 4.5 hours. So if we want to fully degrade this 50 ppm, then actually we need longer time for the photocatalytic degradation to happen. But it is expected because we have a higher number of pollutants, right, at this 50 ppm. Okay, so the performance of the 5 ppm is quite good, while for the 10 and 15 ppms, we find that the performance is quite moderate, while the performance of the 50 ppm is quite low. Okay. So what we can see actually to reduce the gap between the 5 ppm and the next concentration, which is 10 or 15 ppm, we actually need to do more thorough research, yeah, in terms of the distribution of the materials inside the fiber, right? Whether the materials actually still has the same surface area that still can be accessed by the organic pollutant when it is in the immobilized mode rather than the non-immobilized mode. Okay. So further research still needs to be done related with this performance, right? But so far, right, but what I can conclude by utilizing the carbon quantum dots, especially for the photocatalytic performance, right? Based on our result from doping, we can actually tune the photoluminescence properties, yeah, from this carbon quantum dots. So we can actually modify it into the material that has blue shift or red shift, right? But the sole use of the carbon quantum dot itself actually does not really give a satisfying performance, yeah, for the methylene blue degradation. So we can reach up to 80%, yeah, for the methylene blue degradation. So we think that the more versatile application of these carbon quantum dots, we can actually combine it with the other photocatalytic agent, yeah, such as titania. So in the case of titania, when we combine these carbon quantum dots with titania, we actually can degrade the acetaminophen under sunlight irradiation. So after 4 hours, we actually can degrade around 5 ppm of the acetaminophen. When we increase the acetaminophen to 10 ppm, then we need around 6 hours to actually degrade the pharmaceutical agent, yeah, under sunlight irradiation. Okay, so we also try to combine the nitrogen dot carbon quantum dots with tungsten oxide, and the performance of the methylene blue removal is actually better. We can reach around 97% removal, yeah, and even after we actually reuse it after 3 cycles, we can still achieve the methylene blue removal of more than 80%. And then this material, yeah, experience immobilization, right? So we immobilize it into the fiber, yeah, the polylactic acid fiber. So we manage to be able to be used for the oil-water separation. So we can actually improve around 87% of the oil-water separation, yeah, in comparison with just PLA fiber, yeah, in comparison with just PLA fiber. And the colorization performance actually improved by around 31.62%. Right? For the oil and water separation, yeah, we can actually improve the performance of the fiber, yeah, more than 100%. So from here, we can see that the incorporation of the carbon quantum dots into the photocatalytic agent matrix not only limited to the photocatalytic degradation, but it can also be extended to other type of application, such as oil on water separation. So we hope, based on the experimental results that we have gained, we can venture in actually optimizing the experimental condition, especially for the oil and water separation. Maybe we can actually test it for different type of hydrocarbon, and maybe one day we can actually test for the oil spill samples itself. Okay. So this closes my presentation about the utilization of carbon quantum dots for the photocatalytic degradation, and I will be happy to answer your question. Okay. Thank you very much.
All right, thank you very much, Dr. Noni, for the very insightful presentation. It's such an exceptional work. And now we are entering the Q&A session. For the audience who has a question to ask, you can ask through Zoom chat feature or ask directly to Dr. Noni. We are welcome your question. Anybody? Okay, can I ask first, Dr. Noni, regarding your work? Yes. Carbon to myself, to me, carbon quantum. I'm not quite familiar with carbon quantum dots. We often hear it in maybe science fiction, but not in real life. And what is the future potential of application of the carbon quantum dots? Is it going to be applied in some area, maybe in manufacturing or energy or something else?
Okay, thank you for the question, Mr. Aditya.
Yes.
The future, I think, for the carbon quantum dot is still strong in biomedical area, especially for the bioimaging right, or biosensing. Actually, because of its luminescence, this kind of material is used as tag. For example, we want to do cancer research, right?
Okay.
For the cancer research, actually, the challenge is we want to have targeted drugs, the one that only affect the cancer cell, not the other healthy cells. Okay, so based on the research so far, how to actually observe whether the drugs only affect the cancer cells is if we use certain tag. So we can actually encapsulate the drugs into the quantum dots, into the carbon quantum dots. And if we ingest the drug, we can actually do the bioimaging. We can see at which position is the drug actually can release its active agents. Right. So this is actually the bioimaging can be done by many other instrument that actually can receive this color that is illuminated or the light that is illuminated by the carbon quantum dots.
Okay. All right. So the current technology is unable to identify whether the drugs is effectively works on the cancer, I assume. Is it correct?
Yes, I think you need to actually still you need to do the surgery after the application of the drugs. But to have the real time on how the distribution of the drugs, to see the distribution map of the drug inside the body, it will be nice if we have some kind of agents that can track the path of the drugs.
So in the future, we will no longer require surgery maybe to confirm whether the drug is work or not with this invention.
Yeah, that is the purpose actually.
Right. All right. yeah, we have some clarity about the potential in the future.
Yes.
So thank you, Dr. Noni Soraya, for giving the clear answer. I'm still opening chance to ask, opportunity to ask for the other audience. Okay, I guess we finished for the first presentation, and thank you very much, Dr. Noni Soraya, and I hope we can meet again in a better state, maybe next year.
Inshallah.
And inshallah, yes.
Thank you
And
very much for
please,
inviting me.
yeah, stay healthy and having a pleasant day. Thank you, Dr.
Thank
Noni
you very
Soraya.
much, everyone. Take care and stay safe.
Okay. Coming up is the presentation from Associate Professor Abdul Hakim Al-Majid. Assalamualaikum warahmatullahi wabarakatuh. Associate Professor Abdul Hakim Al-Majid.
Assalamualaikum warahmatullahi wabarakatuh. Thank you.
How are you today?
Good, thank you, Dr. Noor. And it's my pleasure actually to present behind those audience and the conference. It's a great pleasure for me.
Right. And we are pleased to have you here. And before we start, let me read a short portfolio about Associate Professor Al-Majid. Is that okay?
Sure.
Yeah. Yeah. Okay. Thank you. Oh, I'm sorry, I haven't introduced myself, Professor. My name is Aditya Muhammad Noor. You can call me shortly by Aditya. I'm the moderator for this plenary session. Associate Professor Dr. Al-Majid received his PhD from University of Washington, Seattle in 2002 at the Mechanical Engineering Department. And he received a scholarship from King's University to pursue his graduate study. And he leads a research team he also leads a research team to establish the Center of Excellence for Research in Engineering Materials in the College of Engineering, and was the technical director for the center since the started until 2016. And in 2016, Associate Professor Al-Majid joined Prince Sultan's University as the College of Engineering Dean. And today, Associate Professor Abdul Hakim Al-Majid will present his keynote about titled Development of 3D Printed Socket for Unilateral Transtibial Amputees. So, Associate Professor Abdul Hakim Al-Majid, if you are ready, the screen is all yours.
Thank you very much, Dr. Aditya. Really, it's my pleasure to present for the great audience the work that we have conducted in the development of 3D printing prosthetic. I'd like to present my screen, if it's possible. You see my screen?
Yes, we can see it clearly.
Perfect. As I mentioned, as I'm working now in Prince Sultan University as the college dean, and as part of our community service, we thought about how to really serve the community in an engineering way. And through the discussion, we came up with developing a PC prosthetic and orthotic center that can help the community and also serve the engineering mission and vision. We thought of really going beyond the technical or conventional technology, really how to utilize the evolution coming in recent years, the 3D printing, and really developing these prosthetic and to expedite the time. We tried to collaborate and build alliance with different entities, started from my colleagues in Prince Sultan University, Engineer Bandar Mishari, Engineer TY and Adil Al Yahya and Dr. Munir Page. And also we collaborated with Qna Technology and a non-profit organization that work to serve the developed country to help them regarding the use of CAD technology and 3D printability. And finally, we collaborated with the medical institution, the Prince Sultan Humanitarian City, represented by Dr. Abdullah Zia and Dr. Iyad Faris. Those three groups work together really to develop the 3D printing technology in Saudi and try to test it for our patients. As introduction to the subject, in the globally there are about 1 billion people living with disability, and it's expected to rise to about 2 billion by 2050. Most of them, almost 80% of those, are living in low-income countries. Only 17%, up to 37%, receive assistive devices. The rest are really left without. With the growing need, there considerable, shortfall the technicians that can serve them, and the expectation will be lower by the 220, below 17% will be served. The institution that really produce those technicians and experts on how to develop the assistive product, assistive working product is only very few, only 24 programs running, and as few as 400 graduates per year in low-income countries. So it's really low compared to the needed market, and the market is increasing year by year. So there has to be some strategies that can help in increasing the productivity of existing prosthetics in order to serve more patients. The current technology that is used are mainly for the TT prosthetic. By the way, the transtibial prosthetic represent about 70% of all assistive devices needed by patients. So there is a great demand in really producing more transtibial to serve more patients. And mainly they used the devices that was developed or presented by the International Committee of Red Cross and the International Committee of Red Crescent. The IRC approach is very manual. It uses the plaster of Paris, the gypsum plaster, and propylene. So there are a lot of difficulty using them and limitations that the patient must be on site. And that's really one of the major challenges in the low-income countries. As you all know, in low-income countries, people live in their daily allowance. And to leave their home for a couple of weeks or 3 weeks to do the prosthetic is really a lot of time, and they might not survive all that time to really live on. So to get the patient to the institution is sometimes the most difficult part in dealing with the patient in the low-income country. And another thing, the replication of the devices is mainly almost impossible. Once you make the device from the gypsum plaster, it has to be destroyed. And if you need to build a new one, the patient has to come back again for another measurement. So for that, also that the ICRC is really time consuming. It usually takes about 3 weeks for one prosthetic to be delivered. For all these reasons, if we go to, it takes very long time. I'd like to present here the process it takes for normal or conventional prosthetic. It started with this picture with the patient. As you see, there's a residual limb, and the patient wrapped with the plaster of Paris bandages, and it's to get it wet until it's dried. Then they take off that bandages, and this becomes the negative cast. The negative cast is marked by the prosthetician to identify the pressure points, and then once it's ready, they start to fill it with another liquid gypsum just to identify the inner body of it, and then they put like a metal rod, and finally they get the inner part of it to make the positive cast. So this is the positive cast that was prepared, and it really resembles the residual limb of the patient. After cleaning and preparing, they start to develop the propylene sheets. It is heated into an oven, and then they place the inner connector that need to be connected with the silicone lining of the patient, and then with the heated plaster or heated sheet, they start to mold the socket. So at the end, you would see the right sign. This is the socket, but after the vacuum, you would resemble the needed socket. Later on, they add certain chemicals to build the external connector, and they pour the external connector and then try to break the cast, which is the most critical part. Now, once this cast is break, you need to do a new measurement for the patient, because all measurement has gone once you break it. And then they start to grinding to make it in shape, grind the outer socket, prepare the outer socket anchor, and then later on try to adhesive and drill the anchor cast to the socket, and later add all the accessories, and then connect everything together to make the full socket. Now this is the full socket done with the conventional technology. It takes about 2 to 3 weeks to make for one patient. Then later on they will do some fitting and then modification. So it might take a month for one patient to finalize his prosthetic. The disadvantage, as I mentioned earlier, the patient must be on site. The replication of the devices is very limited and almost impossible. It's a time consuming. The environment there is not really safe. Too many machinery, too many gypsum powders that might cause some inhalation problem, long hospital stay, and the limited productivity due to a long time process. So all these really makes the conventional technology as very time consuming and not really attractive even to a prosthetician to work in. There are lots, great needs for adopt new technology. As I mentioned, the current sockets takes like a long time to make. It's a rate limiting factor. Many strategies need to be developed. New processing methodology should have at least fast production time, better access to mobility, safer work environment, shorter hospital stay, and the idea that has been there for a very long time is how to use the additive manufacturing technology in terms of helping expedite the process of the disabled person to build a socket. So additive manufacturing, which is the production name for 3D printing, computer control that creates dimensional object by depositing material. It is additive manufacturing, so it's really you add layer by layer. You don't really waste a lot of material. So mainly you're just building layers on top of each other. Using computer-aided design or 3D object scanner allows you to create the object without really wrapping the patient with a plaster cast. There are lots of techniques are using many in other manufacturing, laminated object manufacturing, selective laser sintering, fused deposition modeling. It's a lot of activities and a lot of machinery that technology in the 3D printing world. The strategies that has been there for a while is to use this technology with the amputation for in low-income countries and use the scanning, modeling, and printing to leverage the expertise of existing personnel. If we go back in time to check what has been done, we would see that the CAD/CAM system has been there in the early 80s, and there are a lot of activities in really how to develop the prosthetic using this technology. In the 80s, also the 3D printing technology has established. Took a very long time to really, I would say, mature. And in the late 80s, processes started with the FDM printing. So the technology is there. People are working in this area. If any one of the audience would like to go to YouTube, they would find a lot of people worked in developing prosthetics through 3D printing. The work that we are doing and Qna is doing is really how to integrate the medical establishment and do real testing on the patient. We hope at the end we reach a point where we can replace the current technology with the 3D printing technology, but that has to be in collaboration with a medical institution to really approve that concept. So the additive manufacturing process really has 3 different stages. One is the scanning stage, and then the design stage where you take the scan model and customize to fit the patient, and then finally the printing stages and the connectors and building the full structure. If we talk about the scanning phase, you would have taking a scanner. Here we used a very simple scanner, iPad scanner. It's attached to the iPad. The cost is about the whole of the scanner and the iPad. It doesn't cost more than like $1,200 or $1,000. So the idea is just to scan the amputated limb of the patient. Here is just presenting a short video of how to do that. Is the video clear there? Dr. Adeta?
Oh, yes, the image is clear.
The video is working?
It's not moving. The image is not moving.
The video is not showing?
I'm not showing.
Okay. Just I think I need to. Trying to just share the other file, but I don't know how to share it because it's very critical to share the file.
Maybe if it's too difficult, maybe it's better to.
I just no, but I'm trying to. Okay. How to open this. How to stop sharing? I'm just not explaining.
Maybe you can move your cursor to the bottom side of the screen and you can press the green mark share screen button and you can click stop share and reshare again.
Okay. Yeah. So let me
Okay.
just. Okay. If you allow me, I will. Does it show now?
Not yet.
Not yet. Now?
Yeah, it's now showing.
Yeah. So here, I do apologize for that. I'm just trying to show the video. Here is the scanning where we just scan the limb, and then you would see now we're trying to focus, and then later on we can start and then scan the area, and we need to have a 360 to scan the full area. So I'm just showing a short video of this. And then I'd like to share again the presentation. So once we take this is now the file that we take, and it shows really the part of the scanned area and part of other scanned area. Then we need to take it to another software to do the design for the rectification part. So the rectification part can be done through any CAD system, or the 360 with Autodesk or any other software. We collaborated with Qna. They have their own software, and they build a software to look into this file that was scanned and how to do it. So here I'm going to show you now the other file where we had the presentation. So you can see here, this is the Qna software that we use. You have the general information for the patient, and we take the file, and you can see the file. It has really take image of so many things, and we need to focus in the area that we would like to have the socket. We need to adjust the scan and select the area that we would like to use. So we need for the cleaning phase. Now we're taking the cleaning phase and taking the exact part that we would like to focus on. And from that, we align it for the patient with the longitudinal direction. And once it's aligned, then we can start building the socket. Now it's aligned. Then we will have the trim line. I'm going so fast here, but it takes like about 30 to 40 minutes of working with the prosthetician to check the pressure area and to make sure that the location of each point. Here at the back side of the prosthetic. So you can see that you build it, and then with the smoothing line now, it's really ready to developed the socket. Now we added certain millimeters to make the socket, and then now this is the socket ready for printing. It is transferred to STL file, and from that we can print it. Later on, sorry, I'm going back and forth to the presentation. Later on,
No, it's okay.
Since that software that we use really was fit only with the ICRC connector, while our hospital here, they have their own connector. So we tried to add the connector that available in the local hospital here, and we use 360 here to we took the file that we made in the NIA, and then we have it here, and then we add the external connector to the socket, and then that was the internal connector, and then now we developed the external connector. They have two types there. One is rectangular based connector, the other one is anchor based connector, and we develop both. We can add them to the final design, and this is the final design with the rectangular based connector that need to be sent to a 3D printer. So the 3D printing phase, we use the Qna as the slicing software. It's an open source. It's available for everybody. They can use, or they can use their own slicing software of their choice. You need to just set up the parameters, the extruder temperature, the bed temperature, the speed, the printing orientation, the printing directions. In terms of the material, in the beginning, we started with nylon. It was very nice material, very durable, hard. The only problem is happened with the, in the East Asia, especially in Vietnam, where the rice plantation. In the rice plantation, they had a problem where the nylon really absorbed the moisture and the water, and it's really expanded, and it started to build water inside and then break in the nylon. Later, we went to another material. We used the polypropylene, and now we are processing and making sure everything is working properly. I'd like to show the printing phase that we here is the printing phase. Once we send, we use a normal printer. It costs almost $1,000, so it's not really a fancy 3D printer to print the socket. And once the socket is ready, we can immediately use it in a patient. So back to the presentation. Once this is done, we have the assembling of the whole socket with the foot and pylon to make the 3D printing amputated leg. And finally, we had a clinical trial for a patient, and this is the final video I'd like to show. This is one of the patients that we have tested on, and the hospital asked us to really strengthen the top of the prosthetic. They were worried about breaking, so we give them that. But always the hospital think about liability a lot, and they would like to test it. So that was a test, and we were happy to really. That person now is 6 months, and we were having very good positive sign from his testing. At the end, I would like to conclude that it's running very slow, but the 3D printing really have revolutionized many aspects of medicines, and there is a lot of activities are conducted And I wish that the experience we have can be expanded in many other countries and they can test it. It's not just an engineering point of view, but it's really a time point of view. It's really going to increase the productivity, reduce the time. Here we run it in about almost 24 hours from the patient receive the hospital until he gets the prosthetic. It's only 24 hours compared to 2 to 3 weeks in the conventional technology. And the price-wise, it's really becoming very cheap. The machinery is really about $2,000 to $3,000 cost. The socket itself, it doesn't go more than $100, $150. There is a lot of advantages of using this technology, as I mentioned, faster production time, the high mobility. You can even have a mobile clinic that can go around the country with a scanner and send this data to a centralized location for printing. So all you need is an iPad with the prosthetic to go around the country and visit other places. You can build a clinic in every hospital with only very limited equipment. It's a safer work environment. There is not a lot of machineries. There's really very few to work with. Short hospital stay, as I mentioned, it's a cost saving too. And they are very customized. That's the thing that is really you will never have in other technology. I had a patient who would like to have his Manchester United logo in the prosthetic. So it is really something that make the patient feel good of having such a prosthetic rather than getting embarrassed walking with it. And many people really get proud. People look at it and say, wow, this is something, rather than feeling pity. So there are a lot of things, and I'm sure, I hope the wheel will start moving in any other location in the world to start developing similar ideas or even better ideas. Thank you for listening again.
All right. Thank you very much, Associate Professor Abdul Hakim Al-Majid. Such a remarkable work that you have done. And now we are at the question and answer session. For the audience who has a question, you can ask directly by unmute your microphone. Anybody? All right. So, Associate Professor Abdul Hakim, may I ask the first question?
Sure.
Yeah. In terms of, so I saw in the video that the socket is used by a teenager. So compare with the conventional, maybe clay socket and 3D printed socket, is it any difference to the, is it any effect to the person's growth? I mean, the teenager's growth. While using the socket, he's still growing, in the growing age. So is it any difference of effect between the conventional and the ones that is 3D printed?
Well, the conventional is at the end, they use the same material. It's a plastic material, but the process itself, we build it directly from the scanning part, and then modification part, then the printing. While in their way, they use the plaster cast or the gypsum powder just to identify the mold, because they cannot find the mold only by rubbing the leg with the plaster of Paris gypsum. They can find or they can identify the size of the amputated part or the residual part. So it is at the end you would deliver almost the same thing. Sometimes I'm not criticizing their workforce; they're doing a great job, but it's a time consuming. It takes a very long time. The material they're working with, especially the gypsum, might harm their health. Using advanced technology that will really shorten the time from days to 1 day, or from weeks to days. That would really help in serving more patients. Uh, right now, I have read about in the Philippines there are about 2 million people with a need for prosthetic limb, while only they can serve about 1,000 to 2,000 per year. So you can imagine the need versus the availability of prosthetics. So the major advantage here is definitely using the technology, but it's not about the quality of the product. It's about how fast you can produce it and how many you can produce in a month compared to how many you can produce in a conventional technology. In many areas, some people like, if you go to handmade, it's cost more maybe in every case, but it doesn't mean it's a better quality than the automated one.
All right. So far, do you receive any feedback regarding maybe the comfort from the user?
Yeah, the patient I have presented has been like 6 months wearing it and had show great responses. We are in the phase now of testing 10 patients. Hopefully, by end of the year, we can get the feedback regarding how they feel about it and what need to be corrected to fix the issues. We are focusing here in below the knee amputee, which correspond to about 70% of the population of the people who needs assistive devices. And if we can cover some part of that area and reduce the number of patients, here in Saudi, we have around 40,000 people in need for assistive devices, and the maximum they can deliver in 1 year is about 2,000, the hospitals. So probably 20 years, that's not including the additional people who are coming from either accidents or from diseases like diabetes or others. So there is a big lag in terms of the productivity and the need.
Right, we get the point. Yes. Okay. Thank you, Associate Professor.
I do apologize for the technical problems of presentation. I thought I would present everything at once, but it wasn't there.
It's okay. Don't mind about the technical problem. We still receive a good amount of information from you. Yeah. Okay. Is there anybody else who wants to ask a couple of questions, maybe? Okay. It seems there's no more question. So, okay, it's a really pleasure to have you here, Associate Professor Abdul Hakim Al-Majid. I hope we can see you again in the better state next year, perhaps. Yeah. Thank you very much for your time and for your knowledge that you have shared with us. Stay healthy. I hope you are stay healthy and have a pleasant day. Thank you very much, Associate Professor Abdul Hakim. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much.
And for the audience, I have a short announcement that you are advised to return to the main room for our announcement that we are going to have shortly. Thank you.
Okay, all attendants may come back to the main room via the links in the main room. Like this. Okay, please join to the main room.